morning. Here in Germany, it's quite early already. I think we can start, I guess. And gladly you can see my screen. So yeah, welcome everybody to this presentation of mine. And today I'm presenting some key insights from our paper, Workload Characterization for Resource Optimization of Big Data Analytics. Best practices, trends, and opportunities. Also, thanks for the introduction. And this is a joint work with my esteemed collaborator, Alexander Guttenberger, and we are from the Technical University of Berlin in Germany. Okay, so this is the outline of my talk. I would like to start with a brief motivation, then follow up with a problem description. Would then briefly talk about our research methodology and then dive into the analysis and some interesting findings that we made. And of course, then also discuss the potential threats to validity just out of transparency and conclude the talk. Okay. So we are all aware of the fact that these days and also over the last years, large volumes of data are generated and require processing. This is generally known as the age of big data, or these days big data and AI. And usually for the processing of these large data volumes, data processing systems are used, and they are usually distributed systems. So the computation is handled over many compute nodes. Now, the point is that over time, many of these frameworks have been developed and proposed. You can see also some of these here on the slide. But the configuration and the optimization is non-trivial, even for experts, because there are many configuration parameters you have to consider. And then on the other hand, we have more and more people from different domains that require data processing, but they are not necessarily expert in these systems. This could be scientists from other domains or small, medium enterprises. So in general, we seek automated solutions for configuring and optimizing these systems. In here, from our perspective, in terms of resources that are necessary to run these systems and workloads. So we take a perspective where we are interested in resource management, adaptive resource management, and how we can optimize this for various workloads. So generally, we have to, of course, be aware of certain challenges that exist and that have to be considered. So on the one hand, we might have changing data volumes and characteristics, so distributions and the data that needs to be processed. And this, of course, also can impact how long a particular job is running, how much resources are needed. Then, of course, the individual workloads can have different parameterizations. They can also use different algorithm implementations. And this, of course, can also impact on performance and, for instance, runtime. And then, of course, it's also very important where these jobs or workloads are executed. So is it happening on some local hardware, some on-premise cluster? Is it in the cloud where we are most likely using or relying on virtualization? And of course, then aspects like isolation and interference are also increasingly important, but also the cost that are incurred by running workloads in the cloud. And then, of course, we also have changes in degradations over time. So while you are executing a long-running job, it might be that you have changes in the data distributions. It could also be that you have co-located workloads, and this, of course, can also influence the execution of your particular workload. So usually, how is this problem addressed when we want to automate this? Well, usually this is done using performance modeling. So you try to relate different parameters to an outcome, like a measurable outcome, some golden signal you're interested in. And here's an example on how you can, for instance, select a scale out, so the number of machines or compute nodes based on runtime targets. So assume you have a static workload and you're executing it with a different number of machines. Then you measure the runtime. Then, of course, you can relate the number of machines to the measured runtime and then use this very simple relation to some degree to predict how long the workload would require for a different runtime. And then you can, if you have certain performance targets, choose based on these targets. The problem is usually this requires a lot of data to train on. So you need historical performance data, or you need to have sufficient time or budget to do some kind of initial profiling. And often parties or users, they don't have either of them. And then at the same time, they often operate on the same infrastructure or they employ established frameworks. So these days, many workloads are run in the cloud. And so, of course, if you manage to learn how particular machine types are working, you could maybe leverage this information. And also, many of the workloads are implemented in established frameworks. And of course, they are also operating in a certain fashion, which you might be able to exploit. So in related work and also our own prior work, we attempted to leverage such related data from related or presumably related workload executions and then exploit these similarities in order to improve performance modeling for a particular workload. And then the idea was that you can use this related training data to calibrate and refine your particular target model. And ideally, this would improve resource efficiency because you can make more fine granular decisions and then also as an effect reduce cost. And then the right hand side is for instance an illustration from one of our previous works where we try to show that assuming that you want to predict the incurred cost by running a workload on a particular machine type, this is in AWS, then of course, if you only have a few sampling points, it's very difficult for a simple model to understand what might be the cost for different machine types, and then there's high uncertainty. Whereas if you manage to get or gather data points from related workloads, you might be able to calibrate your model and thereby reduce the uncertainty in certain regions. The point here is that this is fairly unexplored still because there are some methods that try this, sure, but they make it either part of their modeling and then it's kind of a black box and we don't necessarily know what's going on here. And then we have, of course, some approaches that utilize some idea of high level similarity metrics to kind of use other workloads and their data to calibrate a target workload. So here it really makes sense to seek a systematic analysis and also some kind of evaluation framework in order to understand how we can approach this in a very systematic way. So the statement here we wanted to address is really what are the key workload characteristics commonly used in established performance modeling techniques for distributed analytic computing workloads. So this is here the focus. And how can they be categorized and how do they then affect the creation of sophisticated performance models? So our goal here was to start with a systematic literature review and analysis and then use this as a foundation for creating new models potentially in the future that are able to leverage this cross-context data. Okay. So now talking about the research methodology we applied, here we wanted, of course, to follow a very structured approach for the systematic literature review. So, of course, we first defined the review scope, and here the area was very clear. We looked at performance prediction models for distributed big data workloads, or more generally phrased distributed analytical workflows. And the goal was to provide a structured overview of the workload characterization techniques in this field. And then, of course, there was a certain phase where were conceptualizing the topics. So we identified core concepts for crafting an initial keyword strategy that we could then apply in identifying relevant literature. But this was, of course, an iterative process because not necessarily these initial keywords were comprehensive enough. And then we added this and tried to make this query more sophisticated. And we tried to, in these selected keywords, also include particular techniques like dynamic scaling, auto scaling, dynamic adjustments, but also particular systems that are used for big data analytics, for instance, Apache Hadoop, MapReduce, Spark, Flink, these kind of established systems so that we have like a holistic perspective on the topic. And then we, of course, followed up or followed through with the literature, the actual literature search. In here for the identification of relevant literature, we use the Web of Science database because as a primary source, because there's also research on this that it is a favorable source in the way in how you can search literature and also in the deterministic way of retrieving results. So this was, of course, a good thing here to consider. And then after that, we went through a rough screening and evaluation of the eligibility. So we looked into only selecting publications from peer-reviewed journals and conferences, of course. So there must be a certain quality standard. And then, of course, English language so that it's accessible for most of the people. And we here especially prioritized studies that used empirical research methods because we were interested in actual results, measurable outcomes. We also focused on studies that involved open source distributed platforms just to reflect current best practices and industry standards. And also, most of these commonly used frameworks are actually open source, as can be seen by many of them being adopted and managed by the Apache Foundation. And we try to only look at studies that use non-outdated technology because, of course, there are certain frameworks that have some initial versions which are no longer really used. And of course, this is not something we also have to consider here. So after this, we went into an in-depth assessment of these selected studies and further filtered them. So we read the text, we looked at what kind of parameters were they using, what kind of models were they using, and then based on these filtered results, we finally also used a forward and backward search where we used the 10 most cited papers out of these selected papers. And then we used a tool, some of you might know it, it's called connectedpapers.com, where you can derive and visualize connections. So what kind of papers have been cited by this particular paper, but also what kind of papers have cited this particular paper. And so this helps you to close some gaps that you might have and allows you to capture a wider range of related research. So as a result, we identified with this approach 62 scientific papers and thereby performance modeling approaches. And just out of transparency, this has been conducted in the first quarter of the last year. And then, of course, after that, we went into the analysis and deriving insights, writing the paper. So now let's look at the literature analysis I just hinted at. So first, we looked at all these performance modeling parameters that were used in these papers, and we tried to classify them into black box, white box, and gray box. In here, we followed a very simple distinction. So can a particular parameter be observed or configured without access to a particular framework or without it being very platform parameter specific? If yes, it would be a black box parameter. If no, it would be a white box parameter. And sometimes if it's just specific to a particular framework, we would label it a gray box parameter, although this terminology with respect to gray box is not very established and clear. And so let's just take it with a grain of salt here. But most parameters, I think we can say here, also in retrospect after our analysis, are not black box. So many of the existing approaches are using either gray box or white box parameters because they make use of the internals of particular frameworks, which also, of course, has some drawbacks because it makes these methods not easily reusable for different frameworks or slightly different use cases. All right. So after that, we have these parameters classified, and then, of course, we can associate these parameters also with different layers. So if we look at it from a bird perspective, then if we are running a particular workload, a big data workload, we do have some levels to it. We do have the big data framework itself. We do have the data, we do have maybe certain aspects related to virtualization, to the workload itself, which is here called user application, to the hardware, so the underlying infrastructure that is used, but also the performance, so the measurable outcomes and the golden signals. And now these here are, of course, also important, and we can associate these parameters with these 5 or 6 layers. And they can also be loosely classified. So if, for instance, all the parameters that are associated with a particular layer are of a particular type, let's say gray box, then you could also say, okay, this is a gray box layer, although this is even more difficult, this classification, as it is with the parameters. So also take this with a grain of salt, but it gives you a first idea on what are the different influences when doing performance modeling. Where do these parameters stem from? And what is their impact on the actual performance we want to model? And of course, it might be related to a particular platform. It might be related to the data, its characteristics, but it might also be related to the specifics of a particular workload and the parameters that configure this workload in the internal algorithm, or the capabilities of the hardware that is employed. But we will look into this in a moment. So for the big data framework layer, the question really is, how does the framework operate, and how is this can this be instrumented using these parameters? And here we saw that in 45 of these performance models, we saw that they used this big data framework layer. And this includes characteristics that reflect the internal behavior of the platform. And because they are very specific to a particular platform, this is considered a white box layer, because usually you have, for instance, parameters for Apache Hadoop or Apache Flink or Apache Spark, but this is a parameter that only applies to one of these frameworks and can't be reused without any modifications for another platform. So this is why we call this a white box layer. And this, on the one hand, allows for very fine-grained perspective and accurate modeling, because you know how, for instance, particular stages or tasks of your execution graph relate to each other, but it is also very difficult in reusing this for other frameworks. In here, if we look at the research and also in this 45 publications, we see that there's a frequent use in the past of this particular layer. So there has been a tendency to white box approaches. And the most commonly used workload characteristics are here the framework configuration, which is a very difficult problem. For instance, if we look at, I think it was Apache Hadoop with at some point up to 190 parameters that you can configure. Of course, this is very difficult and you want to assist users in doing that. So framework configuration is, of course, one characteristic you have to keep in mind. And then also workflow structure. So how do different stages of your workflow depend on each other? How do certain tasks talk to each other? What are certain communications patterns? This is something that also must be considered. Then we also, of course, have the data layer. So what does the data look like, and what are its characteristics? And here we saw that it's used in 28 of these performance models. And here we have to say that most studies focus on data size and only few consider fine granular statistics. So the idea is usually, okay, let's say we have 10 gigabytes of data and it takes 10 minutes for execution. Then if we have 20 gigabytes of data, it's 20 minutes of execution. So often you see like a linear projection of how would take more time with more data. And of course, also it's difficult to observe these more fine granular statistics, but because it would require some kind of analysis that you have to do in advance, and it might induce more overhead. For instance, if you want to compute certain distributions of keywords in a text that you are processing. So due to this mix, yeah, this is considered a gray box layer because, for instance, data size, usually something that can be derived without really looking at the data itself. But if you want to obtain fine granular statistics, you have to do some kind of analysis. So this is considered a gray box layer here. So what for the virtualization, we are really interested in how does it affect the workload execution. And here we saw it's only used in 8 performance models that we looked at, but also we have to keep in mind here that in the early days of big data analytics, many workloads were executed on private clusters. And also, only in recent years, we see a shift to cloud computing. We see a shift to managed computing environments by cloud providers. So I think this is also about to change in the future. But this is relevant here because many of these established frameworks are using Java, for instance, or have been implemented in Java. And of course, increasingly, these workloads are shifted to the cloud. So cloud computing is an important aspect here. And just to give some examples for this layer, it might cover JVM parameters, so Java Virtual Machine parameters. But it's also interesting because it depends if you're using an actual virtual machine or a lightweight container. And then you have questions related to isolation, efficiency, startup time. And so this might be very important. And it could also include information like pricing. So how much do you pay for particular instance types per hour or per day? Do you use spot instances? So all these information might be interested or important for a particular model. And also here, due to this mix, we consider this a gray box layer. So what about the user application layer? So how is the actual workload parameterized? And here we saw that this layer is used in 12 out of these performance models. And here the parameters often relate to applications' computational requirements. And just to give some examples, it could include input parameters. So let's say you have a job that is just computing a number of clusters like in a data set, then one parameter would be the number of clusters or the convergence criterion when to stop computing. Okay, so these parameters are of course important and might have an influence, but also the general application types. Is it IO intensive? Is it CPU intensive? And the name could also already give you an idea on what kind of workload this might be. And usually this can be easily derived. So this is usually considered a black box layer because all the associated parameters are black box parameters. And generally, this fosters generalization, right? Because if we use this information on a very high level, we could use it for one framework, but also for another framework. And so there is usability, it fosters also reusability. So for the hardware layer, the idea is what is the underlying infrastructure like? What are its capabilities? And here we see also it's widely adopted in 30 out of these performance models. And it enables a basic understanding of the system's capacity and the performance limits. Just to give some examples here, it usually includes something like the number of compute nodes. So the degree of parallelism of a particular workload, essentially, but also the CPU specifications. So how many CPU cores do we have? How much memory per worker node? All these kind of things. And also this is relatively easy to obtain and it doesn't really require some invasive monitoring approaches. So also usually this is considered a black box layer in our classification model because most of the parameters that are associated with this layer are black box parameters by our definition. And then lastly, the performance layer. Here we have these measurable outcomes and the golden signals. And here we also see widely adopted 32 out of in use in 32 performance models. And this includes historical or real-time data for the distributed workflow. Examples are latency, could be on the network link, but also just processing in general. Also like success rates for tasks, arrival rates, these kind of things. And here it really depends on the granularity of the performance metric you are measuring. And because of this mix, it is usually a gray box layer. So some things like latency, like the runtime of a job, you could measure without having any access to the data. But if you want to compute success rates of individual tasks of this job, usually you require access to the framework. And so then this makes it a white box parameter again. And so this is, in summary, a gray box layer. And typically the other layers influence this performance layer, right? So if you have changes in your data, if you have changes in your hardware, it also impacts the measurable performance. So if you have better hardware, of course, it might be that latency goes up or goes down. Could be both. One other important thing here to consider is that the application type and the requirements also affect the performance. So do you have a CPU-centric workload where it really is all about the coordination overhead or the task execution time? Or do you have an IO-centric workload, which is typical for these big data analytics workloads, but then you can still differentiate between heavy or write heavy? Do you have a communication-centric workload that does it need to synchronize after each iteration, or does it do some kind of bulk synchronization? What are the communication patterns like? Is it all to all to one, so some kind of reduced step? And then, of course, also memory-centric applications might behave slightly different. I mean, many of these second generation data processing systems are in-memory systems, but then it still is important if do you have enough memory or do you have to offload some of these results to disk? This, of course, also then impacts performance and is also always important to keep costs in mind because memory is expensive, as we know, and thereby one important aspect here. So here also all these numbers I just said or mentioned, we also see them here summarized again in the top left corner. And then maybe just some follow-up information here. What we also want to share here is usually these layers are not used standalone. So usually we see combinations of layers. And the most common combination is the big data framework layer with the performance layer. It has been used 10 times in this particular combination, which makes sense, right? Because you have these very fine-grained parameters of the big data framework, and then you have the measurable outcomes from the performance layer, and then you can relate this to each other. And generally, we can say that if we combine layers, it improves the prediction accuracy because you capture more aspects of the workload execution in general, and it gives you a more holistic perspective. But of course, also it increases complexity then. We also saw one trio kind of where we have data characteristics, hardware information, and performance information. And this is an interesting black box combination where we try to do not be so reliant on white box approaches and thereby foster reusability. And maybe just one interesting side note here is that virtualization and user application layers are underused so far. I mean, we have seen in the past years a slight increase in these two layers, mainly because of the shift to cloud computing, but also because of this idea of reusability and performance modeling. Whereas, as I said initially, in the like in the initial years of performance modeling in this particular area, there was this focus on white box approaches, which are not really reusable. And just some more information here to share. We also try to, at some point, plot these publications over the years. So we selected from 2016 to 2023. As I said, we had made this review in 2024. And then we tried to illustrate the percentage values and the proportions here. And what we can see is, yes, the big data framework layer is quite stable, is used in many approaches also over the years. So there's not that much of a big shift, but it's slightly declining in recent years. And we see, on the other hand, the rise of layers that foster black box models. Okay, so we do see hardware layer here being more used in recent years, but also the user application layer, and of course also with our own research we did over the last years, we see an increase in this particular area. And the data layer is also one thing to keep in mind here because it can be seen as a crucial aspect because it allows for a better understanding of the data you are processing and thereby tweaking your workload in a way that it's more suited for this particular data set. And then, as I also said previously, with this shift to cloud-based systems, we see an increase in virtualization, although it's not 100% correctly reflected here. which might be also due to some factors which I will discuss on the next slide. But yes, there are interesting trends here to observe. Also, the user application layer is gaining relevance because it also enables a black box perspective and a reusability of data points, maybe even collaboration between small and medium enterprises or scientists that don't really have many profiling points on their own, but they can, as I said on the motivation slides, leverage information from other related workloads. Just to briefly catch up or talk about these threats to validity, of course, I mean, we followed this very structured approach, right? But it's just fair to also discuss certain attack vectors just to be critical with our own work. It could, of course, still be that there has been incomplete coverage, that some of the relevant studies may have been missed. In fact, being quite or being familiar with many works in this field, I know for a fact that one or two works have not been identified by these search query, even though it has been tweaked many times, which is also why we included this forward and backward pass or search at some point. So maybe here the database has not always been very clear, which brings us to the second point. There might be certain limitations in the database, although it's still a very trustworthy source. There could, of course, also be a certain bias towards the search terms we used in our search. So we could, of course, also further refine that and thereby maybe capture more literature. And then, of course, as I try to highlight here and there, this classification, especially for the layers, is very difficult and at some point, of course, also subject to a certain bias. I think for the parameters, it is more clear, but for the layers, it's not that straightforward. So, of course, you always have to take this with a sort of grain. And there's, of course, always a certain risk of misclassification because you're reading carefully these studies, but you might just not get the information that the respective author tried to convey, maybe because it has been written in a certain way, or maybe because some key information have not been provided, and thereby you are forced to a classification that is maybe not reflecting the actual circumstances. So, I mean, I think this is typical to most of studies that are made when it comes to literature reviews, but I just still wanted to highlight this here. And I also think this to some extent explain why this is not 100% complete over here, because of course, some of the publications for 2023 certainly have not yet been indexed by the time we were doing this literature review. And of course, also with the rise of slightly different research topics in recent years, like LLMs and infrastructure optimization, workload optimization for LLMs. There might be also just in general a shift in research focuses and methodologies, and thereby slightly less focus on big data analytics. Okay, so in conclusion, still we derived this 5+1 layer classification model, which classifies these parameters into 6 key layers for the workload characterization and is a foundation to better understand what are influential parameters and where could we also see potential in the future. We see that, especially for hardware and data, they are quite crucial for prediction accuracy. And also, as I said now multiple times, virtualization is increasingly important because we have increasingly workloads being shifted to cloud environments or managed cloud environments. Future work could focus thereby or therefore more on data virtualization and black box modeling, because I think this is still a very promising area and it enables more people access to computation and performance modeling if we kind of if we come up with performance modeling techniques that allow us to share data and thereby mutually improve operation capabilities. So I think these are like some interesting key insights that we obtained from this study. If you have more, if you have questions, of course, you can send them to me. You can also ask them now. And if you are interested in some more of these details, I can highly recommend you to the respective publication. Okay, thank you.